All right, let's get into some calculus with polar equations. So sketched out just a quick little review of just the relationship between the rectangular coordinate system and the polar coordinate system. So in the polar coordinate system, our points are defined as a radius from an origin and an angle of displacement from a ray where we say we have 0 degrees or 0 radians. So an angle, a ray, defined as the origin ray, and then we have an angle of displacement from that point, counterclockwise for positive angles and clockwise for negative angles. And then a radius, a distance away from that origin point of 0. Okay, and then we have some radius going out this direction. So that's what a polar coordinate is. We overlay the rectangular coordinate system, and that same point has an ordered pair xy, where x represents a horizontal displacement from the origin and y a vertical displacement. So that, of course, creates this nice little right triangle that I put here. Let's go ahead and even just outline it. That gives us that right triangle right there, where the two legs are x and y, the hypotenuse is r, and the angle is theta, and we can come up with these 4 relationships. And the 2 that we're going to utilize, this is how we can move back and forth between the rectangular coordinate system and the polar coordinate system. But the 2 relationships that we're going to work with are this fact that x is actually defined as r cosine of theta, and y is equal to r sine of theta. And we're going to utilize that in this way. If that is true, and we were to come across a equation, a polar equation, r equals f of theta, then theta can actually become just the parameter. We can actually say, oh, well, we know what x and y are, the connection back to x and y, and x is just r cosine of theta, y is r sine of theta, which is just a parameterization in terms of theta. So this parameterizes, this is a parameterization in terms of theta. I had to really think out the spelling of that word. Probably, well, who knows? Maybe I misspelled it. We don't know. Okay, so now let's take the derivatives of these 2 with respect to theta, because if you recall from just a section ago, we did all kinds of calculus with parametric equations. So this is opening the door to let us do all kinds of calculus with polar equations, because now we have parameterized our polar equation in terms of theta. So here we go. If we want the derivative, well, we just take the derivative with respect to x, and we end up with this relationship here. Get my highlighter, for dx d theta, and this relationship for dy d theta. That's in the Leibniz notation. You have the prime notation below, the Newton notation if you like that better. And the derivative of a parametric equation is dy d theta over dx d theta. And so we get this relationship for the derivative of a polar equation. Okay. So those are the formulas, but remember, we're really just kind of adding in, we're not even adding anything in, we're just connecting 2 pieces, the relationship of polar coordinates to the xy coordinate plane, and then what we know about parametric equations. So let's get into some examples. Let's use those equations. So let's come down here, set up an example ahead of time, and let's see if I can get it all on the screen here. There we go. Okay, so I got a couple parts to this, but let's start with part A. So consider the cardioid r equals 3 plus 3 cosine of theta. So that does actually fit the family of curves called the cardioids. And so however you graph your polar equations, utilize those skills to graph these. But ultimately, we want to find the tangent line to that curve at theta equals pi over 6. So I'm just going to go through again quickly how I graph polar equations. I showed this in another video, but let's go through. I like to graph actually the theta versus r graph, and then I just use that to help me plot the points. So I just think, okay, so I've got this still on the highlighter there. I have this shifted cosine curve, and so I'm going to be starting at actually 6. It's shifted up 3, and it has an amplitude of 3, so I'm going to be starting up at 6. By the time I get to pi over 2, I'll be back down here at 3, and at pi I'll hit 0, and then I'll go back up again, and so kind of just hitting those key points here to sketch my curve, and then that is going to give me a cosine curve that looks like this. Now, of course, it goes on. That's just one period. And if I needed to plot more than one period, I would. But I do know that one period here will take me one full cycle through the polar coordinate system. And so that should give me the full curve here. Okay. So let's get in there and let's do it. So if we wanted to graph that, so again, this is how I do my polar graphing. I think, okay, so when theta is 0, I start at a radius of 6. So at the ray theta equals 0, I'm out here at 6. And then the radius steadily decreases down until I get to pi over 2. My radius will be at 3. And so a radius of 3 would be right here at pi over 2. And I know that as I draw the curve, it's just a steadily decreasing radius. So it's going to have this curvature. We also have the hint that this was a cardioid, just based on the form and the family of curves. And so we kind of know what we're headed to. A cardioid, by the way, like a cardioid, you can think heart, cardioid, hearts, cardioids. And then we keep going. So now as we're in this quadrant and the angle increases, so as the angle is increasing here from pi over 2 to pi, we are actually decreasing the radius down to 0. So by the time we get here at pi, we're going to be down to 0. And it's just going to, essentially like spin down, get smaller and smaller. At each angle, the radius is smaller and smaller and smaller and smaller and smaller and smaller, and it gets down here. And then we increase the radius in the next quadrant here from pi to 3 pi over 2. Now the radius is going to head back up to 3. So then we're going to be back out here at 3. Oops, that's not 3, that was 2. Back out here at 3. And so we're going to have, and there's definite symmetry here, so it should match at the same rates that it decreased down to 0. It should increase back out to 3 and then increase all the way back out to 6. And so there is that pretty cardioid, that heart shape on its side, okay? And we're asked to find the tangent line at pi over 6. So the tangent line at pi over 6, right, would be, based on my curve, it's going to be like right in here. And I mean, I don't know if I have the exact right rate on those. I just have the general graph here. But the tangent line is, right, I'm going to pi over 6. What we're trying to find is, what is this tangent line right here? Right? That's the tangent line that we're actually looking for. We're looking for the tangent line at pi over 6. At theta equals pi over 6. So trying to figure out what is that tangent line at pi over 6. So we're definitely going to need the slope of the tangent line. If we want the tangent line, we'll ultimately get in there and figure out what the slope and the y-intercept is, but obviously the first thing we need is the slope. So to do that, I need the derivative. So to find a tangent line, I got to start by finding a derivative. So I need dy dx. I want to know what is the rate of change that would give me the slope of that line. So what is dy dx? And we just talked about that a second ago on that other image. And I won't scroll around here too much, but we talked about that on that other image, that's going to be dy d theta over dx d theta based on the parameterization. And we can think of, well, here's my r up here. R is a function of theta. Let's circle it up here in red. R is a function of theta. And so as just a little reminder, I'll just rewrite those so we have them here, that I'll pause the video real quick and we'll just write out those two relationships real quick for dr dx d theta and dy d theta. Okay, to save just a minute on the video, I just copied down those two equations, dx d theta, dy d theta, that we're going to need to use here. And those, again, those literally came out of a product rule for our definitions for x being r cosine of theta and y being r sine of theta. Just applying the product rule to those two and and coming up with these two relationships for dx d theta and dy d theta. So if I need those, I obviously need dr d theta. I also copied r back down here, so we had it right here. I like to just kind of think about that off to the side for a second before I plug into these two formulas. And I would say, okay, so dr d theta, the derivative of that is obviously going to be negative 3 sine of theta. And then we can plug those into these two equations that we're going to utilize. So that's going to be my dx d theta, and this is going to be my dy d theta. And we're going to plug in our dr and our r. Let's copy our r down here one more line too, so I don't have to keep scrolling around. Let's just move that down here. Okay, and so then we just plug those in. So dx d theta, we're going to have some simplification to do here too. So dx d theta is going to be negative 3 sine of theta cosine of theta minus 3 plus 3 cosine theta times the sine of theta. And I'm going to go ahead and simplify that all the way down here as much as I can just to get it simplified so that when I go to start plugging stuff in, I don't have a big messy algebraic or trigonometric function to work with. So dx d theta here would be negative 3 sine theta cosine theta. We're going to have minus 3 sine theta minus 3 sine theta cosine theta, which is definitely going to give me a negative 6 sine theta cosine theta minus 3 sine theta, and then a common factor. I'm even going to pull that out, so that's minus 3 sine of theta times 2 cosine of theta plus 1. I'm even going to get it factored because you guys don't know it yet, but I'm going to, on the second part of this, I'm even going to ask us to find where the vertical and horizontal tangent lines are. So we're going to be looking at finding zeros of these two derivatives, dx d theta and dy d theta. So keeping that in mind, that's coming, getting these simplified as much as I can, and simplifying them down. So let's do the dy d theta, scoot it over just a little bit so I have a little more space, and dy d theta. Dr d theta was minus 3 sine theta times the sine of theta, plus r was 3 plus 3 cosine of theta times cosine of theta. And again, let's get this guy as simplified as we can. So this is minus 3 sine squared of theta plus 3 cosine of theta plus 3 cosine squared of theta here. And I noticed that if these had both been plus 3 sine squared and cosine squared, then I could do some or both minuses. I could do some simplification with some identities, but I'm going to use a different identity, kind of looking at this and thinking, I got these two cosines, why not switch this guy into a cosine too? So let's just make that 1 minus the cosine squared of theta. Again, kind of working with some trig simplification, seeing what we can get here. Minus 3 plus 3 cosine squared of theta plus 3 cosine theta plus 3 cosine squared of theta. And what do we end up with there? 6. We get a quadratic in cosine. 6 cosine squared plus 3 cosine of theta minus 3. And if I pull out a 3, I have a 2 cosine squared of theta plus cosine of theta minus 1. That worked out super nice because that is going to factor 2 cosine theta. Let's see, what do we end up with? Plus and a minus here. So 2 cosine of theta plus 1 and cosine of theta minus 1 are the two factors of that quadratic. Okay. All right. So I did a lot of simplification right there. Maybe not necessary for this particular example that we're working, where we're just trying to find the equation of the tangent line. But I'm going to have us do part B here in just a moment after we finish part A. And part B is going to be to actually find the horizontal and the vertical tangent lines. And to do that, we're going to want these as simplified as possible. So just kind of went through that as quickly as I could for you guys so you could see, just plugging in my dr d theta into my formulas for dx d theta, dy d theta, simplifying them down to a point where I have them in nice factored form. And now I can put it together. And ultimately, here's my dy dx, and I'll even put it in red because that's going to be dy d theta, which I have simplified here on the right. So that's going to be 3 times 2 cosine of theta plus 1 and cosine of theta minus 1. And then divided by dx d theta, so that's a minus 3 sine of theta times 2 cosine of theta plus 1. Okay, guys, so I definitely went through that a little too fast, trying to rush through that, and I just caught a little error here. I noticed that I got my signs mixed up over here when I was writing it out in red. So let's make sure we come back. Never rush through the factoring. So that should be the minus and the plus. I lost a theta there too. I'm getting too zoomed too far out here. Cosine of theta plus 1. So let's catch that little error there and fix it over here as well. So this should be cosine, 2 cosine minus 1 times cosine plus 1. Okay, and then obviously the 3's reduce. I'm going to go ahead and just simplify that so I don't have to rewrite it here. The 3's reduce and we end up with just a minus. I'll just throw the minus in the numerator. So we'll have a minus there. Okay, so let's hop to it and plug in, I believe it was pi over 6 is what we were looking for. So we were looking for the equation of the tangent line at theta equals pi over 6. So I'm going to pause the video here. I'm going to plug in pi over 6, do the algebra, and then I'll throw that up on the screen so that we can see what the derivative is at pi over 6 without having to watch me number crunch through the pi over 6. Okay, so picking up where we had left off, if we wanted to find the equation of that tangent line at theta equals pi over 6, the first thing we got to do is find that tangent by plugging in theta equals pi over 6 to our derivatives. We got to find the slope of the tangent line. And so I did that here. You could pause the video if you want to look at my what do we call that? I don't know that it's a little bit of trig and then a bunch of arithmetic. And so ultimately, though, it works out super nice. It simplifies down and the slope of the tangent line is -1. And that's actually where I'm going to leave it. If I wanted to find the equation of the tangent line, then I'd need to figure out the ordered pair, the point where the xy ordered pair where theta equals pi over 6, and so we would do that by finding, x is r cosine of theta, and r is 3 plus 3 cosine of theta times cosine of theta, and we would plug in pi over 6, and so x at pi over 6 would be equal to 3 plus 3 root 3 over 2 times root 3 over 2 and ... And we would keep going. We'd find the x, we'd find the y, we'd do the algebra and come up with the line. So I'm just going to leave it there. We could continue until we had y equals the actual tangent line, which we already know, -1 plus b. We could continue and figure out b, but we're going to leave it at that. And that slope of -1, if we go all the way back to where we've got our pretty little cardioid up there, that slope of a -1 totally makes sense on that graph. It should be a negative slope there, and it does make sense. So let's go ahead and instead of doing all of that, that's just a lot of algebra actually to finish that out. So I'm going to leave that example, that part at part A. We found the slope, which was the calculus portion of it, and now there's some algebra. And let's instead consider this guy. Part B, what if we also wanted to find the horizontal and the vertical tangent lines? And so we've already done a bunch of the work, and in the midst of doing that work to find the derivative here, I made us go through and actually, like I said, as I was doing it, I went through a bunch of simplification, used a trig identity, on and on we go. But I did that because I knew we were headed towards this part of the example, where I want to find the actual horizontal and vertical tangent lines. And I'm not sure why that turned red, so let's just turn that back to black. We want to find the horizontal and the vertical tangent lines. And so when we find vertical and horizontal tangent lines of parameterized equations, and we're looking at this dy dx, our horizontal, this is again coming out of the last parametric equation section, where we know that our horizontal tangent lines, I'm going to zoom way in on this, our horizontal tangent lines occur when dy dx equals 0. Well, that's when the numerator, that's when dy d theta is going to equal 0, or the numerator. And so that's at when negative 2 cosine of theta minus 1 times the cosine of theta plus 1 equals 0. And our vertical tangent lines, on the other hand, are going to occur when dy dx is undefined. And dy dx is going to be undefined when the denominator, or when dx d theta, which is, if I can get it all on the screen, sine theta, when the sine of theta times 2 cosine of theta plus 1 equals 0. And so that's when our vertical, where we're going to have our vertical tangents. That said, that's as long as, let me write it so it kind of corresponds with each other. As long as they don't both equal 0 at the same place. So again, little note of caution. We'll put it way out here. So, and this is actually one where we're going to get to explore that a little bit. Note, if dy dx equals 0 over 0, indeterminate, right? Both dy dx and, both dy d theta and dx d theta equal 0 at the same value of theta, then that's going to mean do more work. And we're actually going to think about taking a limit of dy dx as we approach whatever value of the parameter that is. Let's call it alpha. Okay. All right, so we'll come back to that in just a second. But first, let's actually figure out when these occur. So when do these occur? I'm going to pause the video again and just solve each of these equations just to save a little bit of time here on the video. Solve each of these just using a little bit of trig, and then I'll come back. Okay, so I just quickly solved those two trig equations. We'd already had them in factored form. It was why I had us actually do all that factoring in the beginning and simplification, so it would make finding these horizontal and vertical tangent lines a little bit easier when we set these equal to 0. And so we did that. As you can see here, of course, the trig functions, these trig equations are periodic, and so these would continue and have an infinite number of solutions. And that's also true actually even in the polar coordinate system. We just continue to trace that as theta increases. We just continue to trace out that cardioid multiple times. And so we'd hit these horizontal and vertical tangents an infinite number of times as theta increases towards infinity. So just to kind of clean it up a little bit, I said, well, let's just focus on 0 to 2 pi. And from 0 to 2 pi, what are the angles that give us those horizontal tangent lines? And so what I found was on the horizontal tangent lines, those are going to occur on the one cycle from 0 to 2 pi at pi over 3 and 5 pi over 3. And then down here, I just stated where exactly those would be if we want to go back and plot where those horizontal tangent lines are. Now, I did not do anything actually with the theta equals pi, because for the theta equals pi, notice that we have at theta equals pi, it turns out when theta equals pi, dy dx is actually equal to 0 over 0. And that is an indeterminate form, and we're going to have to deal with that. So that little highlighted there, I did write that. But for all of the other places where we had either horizontal or vertical tangent lines, the horizontals occurring at pi over 3 and 5 pi over 3, and the vertical tangent lines occurring at 0 and 2 pi. I wrote both 0 and 2 pi out here, but really we've cycled back, and we're at the same point when we get to 2 pi. So that ordered pair is at the r theta value of 6, 0, and then the 2 pi over 3 and the 4 pi over 3 for those two vertical tangent lines. We'll go back to the curve here in just a second and we'll plot those, but let's figure out, because something kind of interesting is happening right here at theta equals pi. So let's figure out what is happening at theta equals pi. And so if we're going to do that, right, I made this note a bit ago, and so now let's come over here and actually deal with that. So when theta equals pi, let's make a little star and let's come over here. So at theta equals pi, we find that dy dx is actually equal to 0 over 0, which is an indeterminate form. Okay. And whenever we have an indeterminate form, we have to think about what is actually occurring there. Is the numerator approaching 0 at a faster rate? Is the denominator approaching 0 at a faster rate? Is it some kind of a balance in between? It's a power struggle. So this is an indeterminate form, and we're going to have to actually use a limit. So we're going to take a look at the limit. We'll have to actually look at it from both sides because it might be different on either side, but the limit as we approach pi from the left of dy dx. So as we're letting theta approach pi, so coming from, say, like, pi over 2 and moving forward towards pi. Dy dx, and our dy dx was, let's fill that in, theta is going to approach pi from the left of a -2 cosine of theta minus 1 times cosine of theta plus 1. This was in its factored form. Sine of theta 1 plus 2 cosine of theta, and definitely equaling 0 over 0. We've talked about that a lot. That's that indeterminate form. But now that I'm in this limit form and I'm saying, well, what is actually happening, right? Like we're trying to figure out what kind of a tangent line is actually occurring here. Is it a horizontal tangent line? Is it a vertical tangent line? Is it neither? What is exactly happening here? So let's go ahead and take a look. So this is going to end up being L'Hopital's rule here, so we can apply L'Hopital's rule. Oh, you know what? Before I apply L'Hopital's rule, I just realized we're in this nice factored form. It's not going to be easy. Be a crazy product rule and simplification. So it would make more sense in this scenario, before I do the L'Hopital's rule, to just head back to the expanded form here. So I'm just going to go back to the expanded form, and the expanded form here would be minus, let's see, 2 cosine squared of theta plus cosine theta minus 1 over sine theta plus 2 sine theta cosine theta. And that's still giving me that 0 over 0. Okay, so got it simplified. Now apply L'Hopital's rule. Limit as theta approaches pi from the left. We're going to have a negative 4 cosine theta sine theta minus sine theta on the top, and on the bottom we're going to have cosine theta, and then product rule here is going to give me a 2 cosine squared of theta minus 2 sine squared of theta. And now if I actually let theta approach pi from the left, what we're going to end up with actually on the top is a 0, and in the bottom we're going to end up with, let's see, we're going to have a -1 plus 2. Oh, 1. Check that out. We actually get 0. And I will make a note here also, this is going to be exactly the same if we take the limit as theta approaches pi from the right of dy dx. We would also get 0. The steps would be actually exactly the same. Nothing's changing here as theta approaches pi from the left or the right. So we would also get 0. So therefore, we can say this: the limit as theta approaches pi of the derivative is actually 0, which makes it a horizontal tangent line. There's a horizontal tangent line that is occurring when theta equals 0. And theta equals 0 at, when theta equals pi, horizontal tangent line at theta equals pi, and when theta equals pi, we're actually at 0. So that is actually at the ordered pair, the r theta pair at 0 pi. So if we wanted to write that in to correspond with what we had everything listed before. So it's kind of gets small if I try to get it all on one screen here, but there's our vertical. So it turns out actually that we have another horizontal tangent line. We would want to add that back in. Turns out through our work that we showed that this was also a horizontal tangent line at 0 pi. So we could add that in. Okay, let's take a look quickly to finish out the video. Let's just go back to that original graph there. There it is, and we can see that we've got those horizontal, vertical tangent lines. We could get them labeled in there. I think my curve is not all that wonderful here in terms of how I graphed it, but if I'd used Desmos, we could really see where all of those are. But you can see right here, that was kind of that interesting place, if I could just highlight it on the graph, that was that interesting place where we didn't really know what was happening there. As theta was approaching pi, what was actually occurring there? Were we having a vertical or horizontal tangent line? Interesting behavior happening on the graph right there. All right, and that concludes this video, and we'll have one more video just talking about taking it, just adding one more piece to our calculus of polar equations, talking about how do we calculate areas and arc lengths.